Introduction. The purpose of this lab was to analyze the magnetic field of a bar magnet parallel to its length and perpendicular to its length and at a point 45 degrees from the bar magnet's horizontal and vertical axis. Using the data of the magnetic field at varying distances, the dipole moment of the magnet was able to be calculated. The magnet's observed magnetic field was then compared to its predicted magnetic field produced by a computational model. So some physics principles we used to get here was the magnetic field of a dipole or magnetic dipole parallel to its axis. This helped us determine what the magnetic field was at a distance that was parallel to the bar magnet's length. This also helped us determine what the dipole moment was. We also used the general formula for the magnetic field of a dipole. This could be used to find the magnetic field at any given location, not just parallel or perpendicular to the magnet's length. We also used the magnetic field equation of a bar magnet that emphasized distance dependence. So for the model, we used a Python program in GlowScript, and we used that to predict the magnetic field of a bar magnet with a particular dipole moment at any point in space. Below is a preview of our final results. So the method, so it's pretty simple. We kind of just put a bar magnet on the table. We put a meter stick that was parallel to the bar magnet's length. We accounted for magnetic north, and then we kind of found the magnetic field at distances parallel and perpendicular to the bar magnet's length using a magnetometer. We also found the magnetic field at a distance that was 45 degrees from the location of the bar magnet. And we obtained some data, and it can be seen right here on the left. This is the data from the parallel axis magnetic field. On the bottom is the off-axis magnetic field data. This kind of gave us this graph right here when we plotted the natural log of the magnetic field on the parallel axis over the distance, the natural log of the distance. We got this linear equation right here, which is super useful. We were able to find the value n in this equation, which was -2.9238. We also found k. Using those two values, we were able to solve for the magnetic dipole moment, which was 1.54 amperes times meters squared. We plugged that value into our computational model right here. Further, we also developed a function that inputted magnetic dipole moment and distance to calculate the magnetic field at a given distance. We also created these 6 arrows right here to represent the magnetic field at 6 different locations. We also created a final arrow to represent the magnetic field at distance 45 degrees from the location of the bar magnet. And that 45 degree arrow can be seen right there, that purple arrow. The other arrows are the other 6 arrows that we created. The quantitative results can be seen on the bottom right here. And so the experimental magnetic field for the 45 degree angle was as it was right here, 0.0001. The computational result was 0.00003976 Teslas. And there's a slight difference, they're kind of similar, and this discrepancy can be attributed to some errors, such as the presence of additional magnetic field sources, such as nearby electronics, frequent rounding errors, human errors trying to properly place the magnetometer at the right location. And some general assumptions we made to get to our final results was that the bar magnet was a perfect magnetic dipole, and that the bar magnet and the Earth was the only sources of the magnetic field in our situation. So some additional questions. So what if we hadn't accounted for magnetic north and we just placed the meter stick randomly? Well, there would be additional magnetic field caused by the Earth that would cause our magnetic field at a given point to increase. And what if we were to stick 2 identical magnets together end to end? Well, the magnetic field, the magnitude would double probably, and the the magnetic field lines would stay the same, or the direction of the magnetic field at any given point. So to answer these true-false questions, when the magnetometer is far away from the magnet, it measures the near zero magnetic field in that x direction. That's true. It falls off greatly with distance. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. That's false. It increases. The position of the magnetometer has no effect on the measured x component of the magnetic field. That's also false. We know it depends on distance. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. That's true. It increases. It gets larger as it gets closer to the magnet. So in conclusion, using fundamental physics principles, we were able to relatively accurately calculate the magnetic field at different distances from a bar magnet. Using the magnetic moment of the bar magnet calculated from obtained data, we were able to computationally predict and visualize the magnetic field of a bar magnet at a variety of points including points at distances parallel and perpendicular to the parallel axis of the magnet, as well as a location 45 degrees from the location of the bar magnet.